And to understand the shift from Raptor 2 to Raptor 3, one must first undergo a mental pivot. Stop looking at the engine as a machine and start looking at it as a packet of data moving through a network. In the legacy aerospace sector, the world of the space shuttle, the SLS, or even the high-end commercial satellite launchers, the production floor resembles a high-end horological atelier. Each engine is a bespoke masterpiece, cradled in a cleanroom for months, tended to by a small army of technicians who treat every bolt and weld with the reverence of a diamond cutter. This is artisanal engineering, and while it produces magnificent results, it is fundamentally unscalable. It is a local build that works on one machine, but crashes the moment you try to deploy it to a 1,000-node cluster. And SpaceX has realized that the engine is not the goal. The cadence of the engine is the goal. If Starship is to achieve Elon Musk's vision of making life multiplanetary, the program requires a fleet of hundreds of ships, each requiring dozens of engines. Simple math dictates that if it takes 6 months to build an engine, Mars remains a fantasy. Therefore, the Star Factory at Starbase, Texas, was not designed to support the Raptor. The Raptor 3 was designed to be consumed by the Star Factory. This is the hallmark of the factory, as the product philosophy, a realization that the assembly line is the most complex, high-fidelity piece of hardware SpaceX has ever built. In the industrial compiler, from dev to production for the computer scientist, the transition from the prototype phase of Raptor 1 to the mass production of Raptor 3 is the literal manifestation of moving from a local dev environment to a massively scalable production cluster. In the early days, Raptor was compiled by hand. Engineers would make hotfixes on the test stand at McGregor, manually adjusting the code, the plumbing, and wiring to solve for unforeseen edge cases. This was necessary for discovery, but it was a nightmare for stability. Raptor number 3 represents the golden master build. It has been refactored for design for manufacturing. In software architecture, design for manufacturing is equivalent to writing code that is not only functional, but also highly maintainable and easy to deploy across different environments without manual configuration. SpaceX has eliminated the dependency hell of the Raptor's internal systems. By integrating the cooling channels and manifolds into the engine's primary structure, they have effectively baked in the libraries that used to be external. And when an engine enters the production line today, it doesn't encounter merge conflicts, those moments in traditional manufacturing where a part from one supplier doesn't quite fit the housing from another. Because the Raptor number 3 is a monolithic, highly integrated unit, the build is deterministic. The factory acts as the compiler, taking raw inputs such as Inconel powder, stainless steel, and copper, and transforming them into a finished executable, the engine, with minimal human intervention. In the high-throughput mandate, solving the bottleneck. In any complex system, the maximum speed of the system is dictated by its slowest component, the bottleneck. In traditional rocketry, the bottleneck was often the turbopump assembly or the complex regenerative cooling jacket, which required thousands of manual brazing operations. If one braze joint leaked during a pressure test, the entire unit had to be rolled back, inspected, and repaired, a logic error that could stall production for weeks. And SpaceX's high-throughput approach treats these bottlenecks as bugs to be patched out of existence. The goal is a production rate of one engine every 24 hours, eventually scaling to multiple units per day. To achieve this, the Star Factory utilizes a continuous integration and continuous deployment pipeline for hardware. In parallel processing, instead of one engine moving through a linear path, multiple engines are in different states of compilation simultaneously. While one set of components is being 3D printed, the back end of the factory, another set is being robotically welded, the front end. Telemetry-driven iteration. Every engine produced is a data point. If a specific weld on engine number 150 shows a microscopic deviation, the source code for the robotic welder is updated for engine number 151. This is real-time debugging of the manufacturing process, the deletion of QA steps. In the Musk philosophy, the best part is no part, and the best process is no process. By simplifying the Raptor 3 to its bare essentials, SpaceX has deleted the need for hundreds of individual quality assurance inspections. If there are no external lines to leak, you don't need a technician to spend 8 hours leak testing external lines. The unit tests are integrated into the manufacturing steps themselves. And the Star Factory vs. the Atelier. To appreciate the scale of this shift, consider the difference in floor space and worker density. A traditional aerospace factory is filled with scaffolding, workbenches, and specialized tooling for a single engine type. It is a stateful environment. The tools are configured for a specific task and stay that way. And the Star Factory is stateless. It is designed for maximum flexibility and rapid reconfiguration. The production line for the Raptor 3 looks less like a NASA facility and more like a modern automotive plant, such as Tesla's gigafactories. Automated guided vehicles move engine components between stations. Robotic arms, similar to those used to paint car chassis, are repurposed for precision welding and thermal coating. And this automotive logic applied to aerospace is what allows SpaceX to treat thrust as a commodity. In the past, a rocket engine was a precious asset, often the most expensive and risky part of a mission. By making the factory the product, SpaceX has turned the Raptor 3 into a disposable high-performance component. If an engine fails during a static fire test, it is not a program-ending catastrophe. It is a failed build that provides data to improve the next version, which is already coming off the line tomorrow. And designing for the machine that builds the machine. Elon Musk has frequently stated that designing a rocket is 10% of the challenge, while building the factory to produce it is the remaining 90%. This is because the factory is a dynamic system with its own physics. It has friction, which is logistics, latency, which is lead times, and heat, which is operational costs. And for the Raptor 3, DFM wasn't just a buzzword, it was a survival constraint. The engine's design was simplified specifically to accommodate robotic assembly. Vertical integration, SpaceX produces almost everything in-house. This eliminates the third-party API problem, where a change in a vendor's specification can break your entire production schedule. If SpaceX needs a different alloy for a valve, they don't file a request with a supplier. They change the import statement in their own metallurgy lab. The scrub of manual labor, every time a human hand touches the engine, the risk of variance increases. The Raptor 3 lack of external spaghetti, the sensors and wires that plagued Raptor 1, means that the final assembly can be handled by machines that don't get tired, don't miss a bolt, and don't require a six-figure salary. The Starship synergies, the factory producing the engines is physically located just a few hundred meters from the high bay where the ships are assembled. This creates a low-latency feedback loop. If the ship fitters find that a mounting bracket is difficult to reach, the factory can adjust the engine's exterior API, its mounting points, within a single production cycle. In the commodity mindset, thrust by the ton, the ultimate goal of the Star Factory, is to drive the cost of thrust down to the point where it is no longer a primary factor in mission planning. We are moving from the era of exquisite systems to the era of industrial abundance. And in the computer science world, we saw this transition with the move from mainframe computers to cloud computing. In the 1970s, a computer was a unique, fragile, and incredibly expensive asset, much like the RS-25 engine. Today, we treat compute as a utility. We spin up 1,000 virtual machines, use them for an hour, and shut them down without a second thought. And SpaceX is doing the same for orbital access. By building a factory that can output thousands of Raptor 3, they are creating a cloud of thrust. If a Starship needs to deliver 100 tons to the moon, it does not matter which 33 engines are on the booster, just as it does not matter which specific CPU in a data center handles your web request. The factory as the product ensures that every engine is a perfect, interchangeable clone of the last. In the economic mode of manufacturing, while other aerospace companies are attempting to catch up to the performance of the Raptor 1, SpaceX has already moved the goalposts to the Raptor 3 and its associated production line. This is the economic moat. Even if a competitor managed to steal the blueprints for the Raptor 3, they would still lack the compiler, the Star Factory. And building a high-performance rocket engine is a feat of physics. Building a factory that can mass-produce that engine is a feat of systemic orchestration. It requires a deep integration of materials science, robotics, software engineering, and supply chain management. The Raptor 3 is the first engine in history to be compiled at this scale, and its existence marks the end of the era of the artisanal rocket. And as we look closer at the internals of this manufacturing process, we see that the speed of the Star Factory is not just about moving faster, it's about choosing the right tools for the right job. The most critical tool in this entire pipeline, the one that allowed SpaceX to delete the external plumbing and integrate the cooling channels, is the strategic application of additive manufacturing. However, as we will see, 3D printing is not a silver bullet. The true genius of the Raptor 3 production line lies in knowing exactly when to print and when to cast. And the transition from the boutique assembly of the early Raptors to the high-speed, automated production of the V3 represents a fundamental shift in how humanity approaches spaceflight. It is the difference between a one-off expedition and a permanent transportation infrastructure. This infrastructure is built on a foundation of advanced fabrication techniques that balance the complexity of the new with the reliability of the old. An 8.2 casting to 3D printing, choosing the right tool.